one direction. And we grow our system like that. And at one point, the size of the basis becomes too large. And that's when we start applying our density matrix projection. So that's when we start truncating and applying the singular value decomposition. Yes?
Yes, can I ask, so can you, another way to say this, if you're keeping the lowest free energy instead of lowest energy state. Free energy in the sense of, so, you get the energy, you have the energy, but then there's an entanglement in a sense gives you some correction to that from the entanglement with the rest of the system. You have the system, subsystem I, the rest of the system is J.
Right.
So there's an entanglement between your subsystem you're looking at. And that is one that entropy correction or TS correction to the energy. Well, you're at zero temperature, but
I'm not sure how you can.
Entanglement entropy.
I'm not sure how you can interpret this in terms of energy. This usually, well, now we know because there's a, we have quantum information theory. These quantum information theories tell us that everything can be formulated in terms of entanglement and entropy, but.
No, but you're making an approximation of the energy, but it's not necessarily an approximation that is a free energy approximation, right? We're not dealing with the entropy of the whole system.
I'm not sure I understand that question.
Okay,
so So at one point the basis grows too large and we start truncating. And we keep growing by keeping in principle, we keep the size of the blocks, the Hilbert space constant. At one point, this is what's called the infinite size DMRG algorithm. Now what we want to do is we want to study finite size systems. So what we do is we grow until we reach that size, that desired system size, and then we start doing the sweeps. And Steve described this. So what we do is we sweep from left to right, and then we sweep from right to left. This gives you sort of optimization scheme to improve your basis. It's kind of a self-consistent iteration. And at each step in this process, you optimize the basis. So now I want to talk about the wave function transformation. So that's the basic DMRG algorithm. Now there is another step that's still introduced, which is called the wave function transformation. It's very useful to speed up the simulations, but it's also crucial for time evolution. And we need to understand how it works. So when we grow a block by adding, say, a spin to the orange block to build our new larger block, we are basically doing a Sorry about that. All right. What we're doing is basically a change of basis. So let's assume that this L matrix here is responsible for this rotation to the new basis. So this new alpha L plus 1 is going to be a linear combination of the alphas of the block L, of size L, with the other spin. And similarly, for the right block, we do the same. When we grow from the right to the left, we have to add this spin to this block. And we have a similar transformation that involves this matrix here, R. All right? So this is just algebra. This is just a change of basis. No secrets there. But now we can use these matrices R and L to transform the wave function from one step to the next step. And we can use that new wave function as our initial ansatz for the Davidson or Langshaw's diagonalization process. So we have our wave function, which is written as a linear combination of states that are written in the tensor product basis of the alpha, the two spins, and the betas. And these are the coefficients. And now we want to write this wave function for the next step as this, where these coefficients are related to the previous coefficient somehow. And the way to do it is by simply applying this transformation on these coefficients. And this is just, you have to get familiarized with the notation, and this is just matrix multiplications, but it's a very great, a very important improvement in terms of performance, and we need this for time evolution, because in time evolution we're going to sweep from right to left, left to right, but at every step during the sweep, we need to keep the wave function from the previous step. So that's what we're going to use it for. I'm going too fast? It's okay? Okay. Another important step is targeting. Steve discussed this, so what we do is we basically, at every step, we have to build a reduced density matrix with the ground state wave function that we find. But this density matrix and subsequently the DMRG ground state, or the algorithm in general, will only grant us a good representation of this state and only this state. If we want to calculate excited states, or we want to calculate overlaps between two states, we need to target these other states. We cannot try to represent two states that have different different origin using the same basis, because it's a truncated basis. Then there's another definition. We see that the error is strictly controlled by the truncation error. When that happens, when we can definitely say with confidence that we can control the error by just adjusting the number of states or the truncation error, we say that this simulation is quasi-exact. Basically, we can get as many digits of accuracy as we want by just keeping more states. When the error is uncontrolled, for some reason, for instance, when we use the infinite size algorithm to find a system, or we try to calculate excited states using the basis for the ground state, we say that the simulation is not quasi-exact. Basically, it's biased or has errors. So now let's focus on the problem of interest here, which is solving the time-dependent Schrödinger equation. We all know the time-dependent Schrödinger equation. We can solve it by, in principle, if we wanted to do exact analyzation, we knew the basis, and we could do it exactly. We could apply the evolution operator to the initial state, for instance, or we could solve it by some integration method, some numerical integration method. Here the problem is particularly subtle because we are truncating the basis. So how do we truncate the basis in a way that we can actually follow the evolution of the state in time? So, for instance, this is just basic theory. Let's assume that we know the eigenstates of H, and we write our Hamiltonian in that eigenbasis with coefficient Cn. And we evolve in time, we get that the state at time t is given by just a linear combination of those states with the phase that is proportional to the energy, right? Now, in DMRG, we're doing this in an arbitrary basis. We're not doing this in an eigenstate basis. So imagine that we have a basis phi now, instead of psi, and we evolve in time this state. You can go through the steps, but basically, we're going to get a linear combination of the basis states, which are multiplied by coefficients that have contributions from all the energy modes. So these coefficients are going to be highly fluctuating, and they're going to have rapidly oscillating phases. So that's a problem we have to deal with. And of course, we know that when we, for instance, apply some perturbation to the system and we start doing time evolution, the ground state is going to get mixed with excited states. And as I said before, we were targeting only the ground state. So how do we guarantee that we're gonna have a good description of the time evolution if we only targeted the ground state. That's actually the problem they had in the first attempt to do time evolution with DMRG. Actually, a couple of years earlier, before Vidal's paper, Casalilia and Marston proposed evolving in time using some integration methods, say Unge-Kuta, Range-Kuta. And they had some success, but the problem they had in their approach is that they were evolving in time by keeping the original basis. So they calculated the ground state, they have a nice basis for the ground state, and then they evolved in time by solving the time evolution, the time-dependent Schrödinger equation, but they kept the original basis. So as I said before, you cannot guarantee that you're going to describe excited states or for that matter, the state at time t using that basis. A later proposal by these authors here was to target not only the ground state, but keep track of the history of the state. So by targeting the state t0, t tau, t2 tau, and accumulating all the information that you're collecting at every time step. But of course, as you accumulate more information, you need to keep more states. You need to grow your basis. This becomes uncontrollable, basically. It works, but it's not optimal. So then comes the adaptive time-dependent DMRG. So the basic idea, as I said before, is to evolve the state from time 0 to time t by applying the evolution operator. And we apply the evolution operator in small steps of size tau. And the idea is that at every step, as you go in time, you sort of follow the basis. You sort of adapt your basis by following the state in the Hilbert space. So imagine that this yellow box represents your Hilbert space. And this blue box represents the portion of the Hilbert space that you're keeping when you calculate the ground state. Now, what Casalilia and Marston did was to keep this portion of the Hilbert space to calculate the state at the time t. And maybe the state at the time t was somewhere here, not here. That's why it didn't work that well. So what we have to do is follow the state by adapting our basis. At every time step, we sort of try to accommodate, to explore the Hilbert space. It's sort of like, it's kind of like sampling, if you will. At every step, you start exploring the Hilbert space around you to see what states you actually need to keep, and you bring those states into the basis. Yes?
I mean, you're saying you want to simulate the time evolution, but of course at the end, you want to have do some particular knowledge about the final state, namely you want to estimate correlation functions. So, I mean, isn't that relevant in discussions? Because, I could, for example, some observables that I measure maybe are much easier to simulate or to, estimate the time evolved thing of it than other observables. I mean, your goal here is a description, some classical description of the final state, or what is the, right? What's the output of the algorithm eventually? Or maybe I could give you states for which I have a classical description, but it wouldn't allow me necessarily to estimate a local observable. So yeah, I mean, is that useful? So I mean, maybe you'll come to that later in the discussion.
Well, basically, what we're trying to have is a variational representation of the state at time t, but we have to, in a truncated Hilbert space. So, we want to truncate the basis, and we want to have the best possible representation of this state.
But for what? What's the measure of success? Like estimate a local observable, calculate the energy.
Well, the energy. In principle, if you do unitary evolution, the energy remains constant. If what you want to do is you want to calculate observables, you want to calculate overlaps, maybe you want to calculate correlation functions. You may even want to calculate time-dependent correlation functions or Green's functions. So you need to keep track of this state and this state at the same time. That's something that
when you optimize, you decide what to keep, by optimizing something which is presumably overlap.
What we are optimizing that is actually, we're always optimizing, following the same,
This is what you do.
the same idea. Basically, we're the entanglement. So we are just evolving by doing this density matrix truncation and keeping the states that have more information about this.
Yeah, but overlap, typically, I mean, the overlap between two states can be very, very poor, even though the correlation functions are, are pretty much the same. Overlap is but anyhow, I mean.
All right.
Are you considering trying on some interaction of these? Is this like a time-dependent Hamiltonian?
Right. I'm going to present later several possible scenarios. So we could have a time-dependent Hamiltonian. We can do a quench. We can do a local quench, a global quench, a periodic quench. Basically, in principle, anything. So the question is how well will the algorithm perform after you introduce a perturbation.
So he's just in a conceptual picture so far.
All right, yeah, I haven't described the algorithm. This is just a conceptual picture. We want to follow the state in the Hilbert space by keeping the volume, let's say, of this blue region constant. And so in order to do that, we have to follow the state in the Hilbert space. Of course, every step here also introduces a change of basis. So we're not always working in the same basis. We're always accommodating, optimizing this basis. So the way we do it is inspired in Vidal's TGBT. So we apply a Suzuki-Trotter decomposition of the Hamiltonian. So we're going to assume that in principle we have a Hamiltonian that is nice, that has only nearest neighbors interactions, and acts on a bipartite lattice. And for illustration, let's assume we are in one dimension. All right. So we can split our Hamiltonian in terms that act only between nearest neighbors. And we have even terms and odd terms that here I colored in red and blue. So what we're going to do, we're going to apply the evolution so to calculate the evolution by applying the evolution operator on the original state at t0. So in principle, one would feel tempted to doing something like this. You can decompose your evolution operator, which is the exponential of the Hamiltonian, as a product of little evolution operators that act only on these links. But this is an approximation. We know that H1 and H2, for instance, don't commute. So we're introducing an error there. That's called the Suzuki-Trotter error. And it turns out that if you do that, it will give you an error that is proportional to t squared. So this is equivalent to a first order Suzuki-Trotter decomposition. So we want to be able to do this in a controlled way. So we want to control the error. And the error is proportional. So we have two errors now. We have the error of the truncation and the error that comes out of this approximation of the evolution rate. So let's see how we can control both errors. Let's start by doing the Suzuki-Trotter decomposition of the evolution rate. You may be familiar with this trick because it's being used extensively in quantum Monte Carlo for decades. I'm going to spend 2 or 3 slides going deeper into where it comes from. As I said before, we have this Hamiltonian, and now we're going to split it in 2 pieces. One is going to be what happened? There's an animation now. Okay, didn't work. Anyway, there's going to be piece A is going to have the even bonds, H2, H4, H6. And there's going to be a piece B that's going to have only the sum of the odd bonds, H1, H3, H5. And now we're going to write down our evolution operator down here as the product of these 2 evolution operators involving HA and HB. And we know there is an extra term that comes from a higher order expansion of the exponential that has a phase that is proportional to t squared, tau squared, and the commutator between HA and HB. And there are higher order corrections with 3 commutators, 4 commutators, and so on. the point is that this term is proportional to t squared. So no matter what inside that commutator, this is of order tau squared. So this is what's called the Suzuki-Trotter, the first order Suzuki-Trotter decomposition. It's equivalent to what I presented before. Now, there is a way to control this error by doing higher order Suzuki-Trotter decompositions. So what we want to do is we want to write this evolution operator, which involves A, HA, and HB, as a product of little evolution operators with corresponding coefficients AP and BP. So we have a product that goes to some orders P, and then this is an approximation, so we have some extra phases coming up here. And these are proportional to h squared, h cubed. Now I changed variables from tau to h. So this is a general picture. So we have terms here that are proportional to h squared, cubed, fourth, etc., etc. So for each each coefficient can be written in terms of commutators, A and B. So what we want to do is we want to kill these terms, these constants, C2, C3, C4, by choosing these coefficients, AP and BP, appropriately. So we want to be smart at choosing these coefficients, and we want to do it in such a way that we kill all the low order terms. For instance, if we want the fourth order expansion, we want to kill all these C2, C3, C4. So how do we do that? Let's look at the first order. Well, first order is trivial. We saw it before. It's just the product of the two exponentials. Let's look at the second order. The second order is it's nice to illustrate this idea. So what we're going to do is write this expansion as a product of these four operators. E to the A, E to the B, E to the A, E to the B. And we want to introduce these factors in front. A, B, little a, little b. Here we put 1 minus A, here we put 1 minus B. And we want to kill this alpha. So we kill the second order correction and we get only a correction of order h cubed. So here we have to do some algebra. Just have to write the right hand term here by using the expansion of the exponential. And we get all these commutators up here. By the end, we end up with a very simple expression, which is here. So this product here can be written as this thing here, plus higher order terms. So what we want to do is we want to kill this coefficient here in front of the commutator, which is a function of A and B. And the optimal choice is A equals to 1/2, B equals to 1, and that gives us this result, which is the formula that we all know. It's very familiar to all of us. So this is the second order Suzuki-Trotter decomposition. And we can repeat this procedure for higher orders, and we can do fourth order expansion. It will become very messy. We have a lot of exponentials. In this case, we start with eight exponentials, and then we want to play with all these coefficients. But it turns out that the problem is soluble. Actually, there are many solutions. And we end up with a formula that is called the Forest-Ruth formula, which is pretty well known for people that do molecular dynamics, for instance, or Monte Carlo. So all these coefficients, now we, instead of 8 exponentials, we have 7. And these coefficients cannot be written in terms of this number here. So, I don't know what's going on here in my presentation. Should do it this way. Anyway, let me try something. That's when you switch from OpenOffice to PowerPoint.
I ask real quickly, what's the trade-off? I mean, what's the trade-off in terms of the order? Why not go to 28th order or something? Maybe let's take out a
It's the number of exponentials that you need to apply. So already, you know, if you're in first order, you need to apply only the evolution operator with the Hamiltonian A and the evolution operator with the Hamiltonian B. If you want to do second order, we want to apply 3 exponentials. First evolution operator with the Hamiltonian A, then B, then A again. And if we want to do fourth order, we need to apply 7 times evolution with Hamiltonian A.
Each exponential costs the same.
And each exponential goes the same amount of time. And this is very general. I'm not talking about DMRG. This can be applied to world line Monte Carlo. So in world line Monte Carlo, you have this checkerboard composition. You can introduce more subdivisions and do higher order simulations. Another way, of course, you know, to control the error is by picking a very small time step. But we want to be able to, well, we have to find a balance, you know, between the size of your time step and the computational cost of doing these evolutions. So let's do the evolution now using, you know, let's look at the actual evolution using these Hamiltonians, this Suzuki-Trotter approach. So as I said before, what we have to do is we have to concatenate these operators. Each of them involves the evolution using even terms or odd terms, links in the lattice. Now, if you look at one of the pieces here, for instance, HB, all the terms in HB commute with each other because they don't have any sides in common. And therefore, you can identically write this as a product of little evolution operators in the links now. So first we had evolution operator in even links, in odd links. Now we take one of them, say odd links, and we can write it down as a product of little evolutions, but acting on the links only. And here we are not introducing any error because these link terms commute with each other. And the other nice thing about this is that these terms involve only 2 sides. And for instance, for spins, the basis for 2 sides is 4 states. And this is a small matrix, 4 by 4 matrix. This is very easy to calculate. And then what we do is we apply first the evolution operator using HA, then HB, then HA, then HB, and so on. So that's the way the Suzuki-Trotter composition operates. So now, just for fun, let's look at the 2-side evolution operator that I was mentioning before. Let's consider, for instance, that we have a Heisenberg model, which we all know very well. It has this is the Hamiltonian, and it involves only nearest neighbors. So the basis for 2 spins, as I said before, we can choose these bases, for instance, up, 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 down, down, up, up, down. And now we can easily calculate the Hamiltonian matrix, which is a 4 by 4 matrix. And we have some terms that only give you diagonal contributions to the matrix, and some terms that give you the odd diagonal contributions. Now, how do we exponentiate, how do we calculate the evolution operator for this matrix? And this is a nice exercise. If you're a Monte Carlo expert, this is trivial. Otherwise, I invite you to do it, just for fun. So what you do is you diagonalize the Hamiltonian, this matrix, and you calculate the eigenvalues and eigenvectors. We know the eigenvalues, right? This is a singlet, 3 triplet states, right? So those are going to be the eigenvectors. And the eigenvalue is going to be -3/4 of J for the singlet and 1/4 for the triplet. So we know the new basis and we know the eigenvalues. We can exponentiate now the matrix in the diagonal basis. It's just the exponential of the eigenvalues. And then we use the change of basis backwards to go back to the original basis. And we obtain, as a result, the exponential of the Hamiltonian in the original basis. This one here. Which is going to be pretty complex, but not not difficult. So now what we have to do is implement this in DMRG. So we have to evolve the wave function. We know that the wave function can be written, in DMRG we represent explicitly the wave function in bases that involve the left block, the right block, and the two sides in between. And this turns out to be a very convenient representation because these link operators act on two spins, right? And we have two spins in here, in between the blocks. So the most straightforward thing to do, or most natural thing to do, is to apply the evolution operator on these sides. And this is a very simple thing to do. So the evolution operator is a 4x4 matrix for these two spins, and we just have to, when we apply it to the original state, we just have to do this a little algebra to obtain the new state. It's just a very simple transformation. And it has a very low computational cost. So let's see how we do it in practice. Let's start with some state. Let's assume that we are actually starting from the ground state, some Hamiltonian. So, and we did our DMRG and we calculated the ground state, and we ended up with, this setup, the symmetric configuration, and a nice ground state. Now what we want to do is we want to start applying the evolution operator. First we introduce some perturbation. This perturbation can be anything. Let's assume we apply some extra term to the Hamiltonian, or let's assume that we flip a spin somewhere, or we bias the system with the chemical potential or something like that. Yes?
For the ground state, doing time evolution is just phase factor, so not very interesting.
Right, that's why we need to add a perturbation to the Hamiltonian or to the state. So if we start from the ground state and we apply the evolution operator using the same Hamiltonian, we just get a phase. That's what you're saying. And nothing happens, because it's an ideal state of the Hamiltonian. That has basically no interest. What we want to do is quench the system, for instance, and see what happens. Apply some time-dependent perturbation, some sudden perturbation, some bias. Maybe we can flip a spin, maybe we can flip half of the spins, apply some protection operator, anything you want. And then you want to start evolving in time, see what happens. So as we're going to see, this is going to have many applications. Now people use time-dependent DMRG to study thermalization, relaxation problems, spectroscopy for cold atoms, different spectroscopy approaches, and so on and so forth. But let's focus on the algorithm now, and then we're going to describe some of the applications and the tricks that we can play. So now what we do is we have to initialize the system to a nice configuration to start doing the time evolution. So what we do is just end up our simulation there instead of in the symmetric configuration. And now we have to start applying our evolution operator. So what we can do is we start by applying this link operator here. And let's assume that now we consider only the even bonds. So we have to skip the next bond and we apply it. So we skip this bond and we apply it here now. And now we skip this one and we apply the evolution operator here between these two sides. And we skip it here and we apply it.
Are you moving to a new basis as
And
you do this?
right, and we have to use the wave function transformation that I introduced in the beginning to basically preserve the wave function from the previous evolution. So
Every time you
So
make
you're
these-
evolving-
Every time you make these moves, you're
evolving the wave
changing
function.
your blue dot in
Right.
Hilbert space
Exactly,
by optimizing what you kept.
exactly. That's what we need the wave function transformation. So we skip this bond now, we apply it on the next one, and we end up there. And now we did is we applied the evolution operator using HA. what we have to do next is apply the evolution operator using HP. So we do a sweep from left to right now, using HP on the odd ones. So each, depending on the Suzuki-Trotter breakup, this sweep represented one of these coefficients in the Suzuki-Trotter expansion. So if we have a second order expansion, we need to apply it 3 times. First we apply the evolution with HA, then with HA over 2, then HB, then HA over 2 again. That's the second order expansion. And if we have a fourth order expansion, we need to do 7 sweeps. Remember the Suzuki-Trotter decomposition for the fourth order. So, as you see, the computational cost is going to be proportional to L and the number of sweeps. The neat thing about this approach is that each term, as we've seen before, involves only the 2 sides that are left dangling there alone. And we can apply the evolution operator basically exactly, very efficient. And this is much faster than doing long shots during the calculation of the ground state. So, any questions about this adaptive time-dependent DMRG? So, yes?
So if you do the time evolution exactly on the true ground state, you do this, is there some guarantee that these things don't diverge or the overlap between today is the same or large or some guarantee like this?
So what we are doing, our way to control the method is by looking at the truncation error. And looking at the...
But for a fixed truncation, if I run...
That's the thing. That's the thing. For a fixed truncation error, you always accumulate an error, but you have to play with the time step and with the truncation error to minimize this error. So I'm going to talk about error.
I think isn't there a paper by Tobias Osborne? He shows in which, if you have the time on the log n, where n is the total length of the chain, you have an algorithm that, follow the time evolution and estimate, the function value of the local observable. He has a view description of that. And he proves it's what the error of the algorithm is. But it's for, logarithmic time. So then it's well behaved. If you go beyond that, I think there's no rigorous estimates.
I'm going actually to talk about estimation of error and propagation of entanglement. Because the enemy here is the entanglement. Right? As you go in time, you're mixing your state with excited states, and things get very entangled. And in order to keep more information or track of this entanglement, you have to keep more states.
So
yes.
So probably the key thing to note here is that in the original DMRG searching for the ground state, if the ground state is somehow weird or not like what you expect, you may have trouble finding it, you may get stuck, and if you calculate a truncation error, it may not mean anything because it's like you're in a different classical state and you just haven't found it. And so you don't, there's a search issue that comes in. Here, if we assume that we've started with the exact state that we want to start in, the truncation error measures exactly the error that we've made in going to the next step. And so we don't have this extra source of we haven't found the state. We actually know how well
The truncation error is like where you cut off the Schmidt coefficient,
Yeah,
right?
the
Okay, and
Schmidt
that,
coefficient.
okay, and then that gives an error. But of course, that assumes you don't know how much entanglement there is in the state. So if you're short times, you can start with the product state, you can estimate there's.
But you'll see how much you're truncating.
Right.
no matter what.
Yeah, okay.
So as entanglement grows, grows, you have to figure out how to keep track of the information you need to guarantee that you're going to have a
No,
good
you
state.
see how bad you're doing, and this is very informative.
Right. So exactly. I'm going to show plots illustrating that later on. So yeah, there are very fundamental questions about time evolution, especially when you have truncated phases. These fundamental questions are, for instance, well, there's some physical questions such as, is the system going to thermalize? Is the system going to relax to some statistical ensemble? or there are some questions that are more concerning the algorithm and the performance of the algorithm. So how the entanglement behaves evolving time and things like that. I'm going to try to address both of them later on. So let's continue with the algorithm for now, and then we're going to illustrate the performance with some examples. So let's start with this extension that we came up with, and applies to Hamiltonians that don't behave nicely, not that don't behave nicely, that are not, nice local Hamiltonians, such as, the Hamiltonian that I showed before with nearest neighbors interaction. What happens if you have next nearest neighbors interaction? In that case, you cannot apply, in principle, the Suzuki-Trotter decomposition the way we did it in the previous slides. So we have to come up with a different approach, and this approach is basically to go back to the original proposal by Casaligna and Marston, evolve the system by solving the time-dependent Schrödinger equation with some numerical integration there. And this numerical integration can be implemented in various ways, and there have been many proposals after this paper. One is to do the composition of the evolutionary vector in the Krylov basis. So you calculate the Langsos tridiagonal matrix, and then you exponentiate this matrix, for instance. This was also proposed by Peter Schmiedegger. And then you can do the evolution using Range-Klasse, which is computationally less expensive. The problem with Range-Klasse is that it's non-unitary, so you have to be very careful when you do evolution using Range-Klasse, that you're not going to end up with a state that has totally, different energy. Of course, we know that the actual evolution is unitary, so it's norm-preserving, and you have a very fine energy. So these are things that you have to look at when you do time evolution. That you're not messing up with the unitarity. So what we do then is, what we propose to do is to go back to Casaligna and Marston approach using Range-Klasse, for instance. But instead of keeping only the information about the initial state or all the states in between, we keep information about 4 states between T0 or T tau and T plus tau. So we somehow calculate very efficiently these 4 states, or some approximation to these 4 states that works for us, and then we adapt our basis using these 4 states, targeting these 4 states with the density matrix, and then we actually do the time evolution. Once we know that the basis is being adapted to the new state at T tau, we actually apply the evolution rate. So first we accommodate the basis. Once we have a nice basis, we do the time evolution. We repeat that for the following time steps, and we forget about the previous time steps. We don't care about what happened in the past. Just worry about the time step between, say, 3 tau and 4 tau. So the way to do it is by using a similar idea as Range-Klasse. We can calculate the state at T plus tau, of course using this famous formula that we all know from basic numerical analysis, or whatever. So it turns out that we need four auxiliary vectors to calculate the new Range-Klasse state. So we need these 4 states, K1, K2, K3, K4, which are given here. It turns out that we can use these 4 states to calculate or to estimate the state T plus tau over 3 and T plus 2 tau over 3. So we only need to calculate these 4 states, K1, K2, K3, and K4, and we can estimate these states that we need to target. So the recipe is very simple. So we do a half sweep. Half sweep means from left to right or from right to left. And as we do the sweep, we keep track of these 4 states in the density matrix. So we need to apply the Hamiltonian 4 times to the state at t tau, and then we can calculate t plus tau over 3, t plus 2 tau over 3, and t plus tau using those 4 states. And we do 1 half sweep. We could do 2. We have to play with the number of half sweeps that we need to do to get good accuracy. But in practice, it turns out that 1 half sweep suffices.
You target those 4 times all equally.
Actually, you can also play with the weight.
Because really, it's the last one you want, right?
Right. So you also have to play with the weight you
Why
put
do you-
on each of them. We actually did that, and we put different weights, and we came up with an optimal
You
choice.
certainly don't want to lose the first one before you've got the last one. though.
Right.
You'd say first one's the most important.
So we put a point, half of the weight on the first one, and 1 quarter of the weight. Half of the weight on the first one, and then we split pretty evenly between the other 2. Yes.
I think that one could mention here, that point is that the density matrix in an interval of time is the integral over this interval. And so in this way you emulate or approximate this integral. And so you get an optimized basis in this sense for this.
Right. You can think it that way. Nice observation. So so we use this strategy to optimize the basis, so to adapt the basis. So instead of having an evolution operator that does it for us, we have to do this thing. Now we have our basis and we want to evolve in time, 1 time step. We can do it many ways. You can pick your method of, your preferred method. One way to do it in the original paper, we applied 10 Rancher-Clavel steps with the time step tau over 10. So that will give us more accuracy by reducing the tau for each iteration of the Rancher-Clavel. Another way is to apply the evolution operator in the Krylov basis, and that's what Peter Schmidt did. And it's actually the way to go, I would say, because it's unitary in a way. I have to clarify that the truncation somehow is getting rid of some of the unitarity here. We're truncating the basis, but still, it's pretty much preserved. So let's talk a little bit about the sources of error here. So the Suzuki-Trotter error, of course, is one source of error. And this can be controlled by using higher order expansions, as I showed, or you can use smaller time steps. So you have to be careful with the energy scales involved in your program. And depending on the energy scales, you want to adjust your time step accordingly. So what you want to do is do many simulations using different time steps and see how they basically converge after the time step is small enough. That will give you an optimal time step. If the time step is too small, you can try doing higher order expansion, and that will give you that would allow you to use a larger time step, but you have to pay the price of doing many sweeps per time step. You have to find a balance. Then of course you have the truncation error, and this is the same error we have in the conventional ground state DMRG. And in principle can be controlled by keeping more DMRG states. So as the entanglement grows, the truncation error will grow. So we can adjust, we can tell our program to adjust the number of states at every time step so that the truncation error is kept under certain tolerance, below certain range. And this in general works, and this is actually the way to do it. We need to adjust the number of states by keeping the truncation error below tolerance. But sometimes the entanglement turns out, for most of the problems we are interested in, the entanglement grows uncontrollable. So in that case, we can simulate to, say, time 10 in order of the hopping, for instance, in order of in units of the the J in the Heisenberg model, but then after time 10, we cannot guarantee that we have a good state. Basically, it's not recommendable that you make strong, you take, you try strong conclusions or you make strong statements about what happens after that time. So then in the Rancher-Kara-Krylov approach, which is the time targeting scheme that I described before, the error is definitely dominated by the truncation error. Of course, you have an error in tau, but this is very, very small. So the main source of error is the truncation. So the recipe that I generally recommend is that instead of fixing the number of states when you do DMRG, you fix the truncation error. And then you let the algorithm determine the optimal number of states that you need to keep. And of course, for some problems, this will imply that the basis will grow to a point where your computer will crash. So that will give you a limitation on how far you can go, what kind of simulations you can do. Some problems are well behaved in the sense that the entropy doesn't grow as fast. You can go to very, very large numbers. So that depends. That's problem dependent. So let's look at some examples here. Let's look at the error here. So we're getting some error here, which is an error in the correlations, and we calculate the error at a fixed time. Here, 18 units of a J. I think this is a spin-1 Heisenberg. Yes, it's spin-1 Heisenberg chain. And we compare to some reference states, which we call exact, which we obtained with the fourth order Suzuki-Trotter, I believe, 1,000 states, something like that. So here we look at the error as a function of the number of states for different approaches. So let's look at first order Suzuki-Trotter. So we know that first order Suzuki-Trotter, the error goes as tau squared. And here we see that as we keep increasing the number of states, the error basically remains constant, doesn't go down. What does it mean? If we cannot improve the accuracy by keeping more states, that means that the error is totally dominated by the Suzuki-Trotter. So, and another thing that we see is that these curves correspond to different values of tau. As we reduce the tau, of course, the error will go down. So that confirms our hypothesis that the error, totally dominated by the Suzuki-Trotter. And the same happens with the fourth order Suzuki-Trotter. So we see that the error goes down initially. That means that we can reduce the error by adding more states, but at some point it plateaus here and doesn't go down. That means that here the error, the truncation error is controlled, but the Suzuki-Trotter error is dominating. And here, for a small time step, we see that it's still going down, but eventually it will plateau somewhere. So we need to play with these two parameters, the number of states and the Suzuki-Trotter time step. Now, if we do what I told you to do, to make the number of states variable, to keep the truncation error under control, then our only free parameter to control the error is the Suzuki-Trotter, the time step, basically. So let's see what happens with the Rancher-Kara, with time targeting. So what we see is that the error basically keeps going down as we increase the number of states. So it's totally, even though there is a difference between two different time steps, here it's totally dominated by the truncation. So it's the other way around. Yes?
Could you just re-explain what you mean by targeting, like when you see target states?
All right. So I need the switch. So we did our density matrix is built, it's defined as states, right? Ground state, typically, when we do the DMRG simulation. Now, we need to target many states, means that we need to write the density matrix as like a mixture of several states. And some of these states may be the ground state, the other states, in case of time targeting, are the auxiliary states for the branch cluster. So, in this case, we're only keeping information about the ground state. In this case, we're keeping information about all these alpha states. So that's what I mean. That's enough.
In one order, is that, the Rongakata has orders which are somewhat similar superficially to Suzuki-Trotter.
Right, this is it. So, of course, Rongakata is fourth order.
It's fourth order Rongakata.
Right, yes.
Fourth order Suzuki-Trotter today.
Right, right. So eventually we might convert to similar bytes, but we didn't go to time. So of course we need to keep, so we are targeting 4 states in the branch cluster. So that tells you that if we want to keep, this, if we want to have the same amount of information about the states, you need to use larger n. Because here we're keeping information about one state only. And let's say 100 states are enough. But here we're keeping information about 4 states. So maybe we need 400 states.
Except they're very similar.
Yes. Yeah, it's not that bad. So it's actually you don't need to keep as many states. It's really becomes very practical. So here we also see how the error scales nicely as we expect for each order of the Suzuki-Trotter. So I'm showing the error as a function of the tau for a given point in time, and you can see that the slopes correspond to the slopes to the order of the Suzuki-Trotter. And this is for a fixed number of states, which in this case is enough to keep the error under 10 to the minus 6 or 10 to the minus 7. And here for Rongakata, we see totally different behavior. See that as we increase tau, here as we increase tau, the error becomes larger. Right? And here, as we increase tau, the error becomes smaller. So that means that, how do we explain that? That for smaller tau, the error is larger. The thing is that for every time step, so if we have a small tau, to get to time 8, we need more sweeps, right? Than if we have it, if we have 0.1, we need, say, 10 sweeps. If we have 0.01, we need 100 sweeps, right? So at every sweep, we accumulate truncation error. And the accumulation of truncation error leads to this behavior. So for a smaller time step, we need more iterations, and the accumulation of truncation error becomes dominant. And basically screws up the simulation. So we have to be very careful and try to find a balance between the time step for the time evolution and the error when we use Rongakata. Yes?
Just one comment or not remember your question, but so you're really, the two sort of variables, one is space, that's a sense, this is captured by how big a state, how many parameters you keep track of, and the other one is time, that's to say how long, how many sweeps do you have to go to, right? And so there you see that the error, you expect that the error, for example, scales the algorithm is still like 1 over tau, right? And that signs that you run it is
Right,
like 1 over
yeah,
tau.
uh-huh. Yes.
Yeah, I mean,
Mhm. Now let's look at the truncation error as a function of time. Well, this is not the truncation error. These are the number of states that we need to keep as we evolve in time in order to have the tolerance, the truncation error under certain tolerance. In this case, 10 to the minus 8. So initially, we start with the ground state, and then we apply perturbation. I think we flip the spin here. And then we evolve in time, the new state with the flip spin. As we see here, in order to keep the truncation error under 10 to the minus 8, we need to keep more and more and more states. Basically, the number of states that we need to keep grows exponentially. And of course, at one point, here we got to pretty large times with 1,600 states. But eventually, this will blow up, and that's when we have to stop the simulation. I don't recommend just an observation, I don't recommend to continue the simulation after you reach, say, 2,000 states. Say, okay, this grows, and when I reach 2,000 states, I keep simulating with 2,000 states. That's not quasi-exact. Mm-hmm.
Question. So, in principle, if you have a problem that involves some sort of thermalization,
Mm-hmm.
wouldn't I expect that after some time, even though you might have some initial growth,
And the
this
separates.
error,
Yes.
it would decay when the system goes back to something closer to the ground state?
Right. If you're lucky, like in those cases, so in some problems where you have relaxation and the system thermalizes, eventually you can have an initial growth, and then you can plateau, or you can even go down
In the finite size system.
in the finite size system.
The infinite system,
Right. But depending on where you're taking, what's your block, where you measure the time. But yes, in the finite system. The finite system will plateau. So if you're lucky, no, what I mean is that if you have an infinite system and you're measuring the entanglement growth in the block here, it will saturate.
So what kind of perturbation is it in this case that you don't observe any sort of thermalization?
Well, let's see how long. This is, maybe I'm not going to times long enough. This is 32 sides. This is a small lattice. And flipping a spin in the center. So it depends on the spin wave velocity, basically. And it's also a gap system, so maybe it should plateau at times of the order of L, but we haven't reached those times. Yeah. Well, what you have is spin 1, you mean spin 1/2, Schrödinger? Yeah, you're going to have a similar behavior. Actually, the entanglement growth, I don't think depends too much on whether you have a critical or a gap system. Of course, the behavior of the entanglement with the distance or the size of your block will depend on whether it's gapped or not. So we have a finite correlation length. So if you have, this is your block L. Let's imagine that we're measuring the entanglement of the block of size L with the rest of the system. If you have a gap system, the entanglement will saturate with the size of the block because you have a finite correlation length. But in a critical system, we will go up. But the behavior of the entanglement growth with time, I think it doesn't depend too much on the nature of the excitation. Maybe I'm wrong. But this is actually a topic of active research, so yes?
So I think it does, the time evolution of the entanglement does depend on the system itself, but for the generic feature, in the finite system you always have a finite size gap, and so roughly they will.
Okay. So let's summarize what we found. Let's compare Suzuki-Trotter and time step targeting. So Suzuki-Trotter is fast and efficient. Works fantastically well for one-dimensional systems. Of course, we need nearest neighbors interaction. If we have next nearest neighbors interactions, we're in trouble. So in that case, we need to use an alternative method. The Suzuki-Trotter error depends strongly on the time step. But of course, we can reduce it by reducing either the time step or the order of the expansion. And the time step targeting can be applied to ladders, systems with complex geometries, long-range interactions. So that's the main advantage of having a method like that. And it has no Trotter error, or it has one, but the main error is dominated by the truncation. Of course, it's more time-consuming. You need to target more states, and it's a trade-off. I mean, still, this is a very powerful method. And Rajikara simulations, as I said before, is a good practice to, basically you have to adapt your basis at every time step. And there are many parameters that you can play with here. You can play on, there's some parameters, I don't know, W alpha here that you can put from, right? And you can play with these coefficients here to see what's the optimal choice. Actually, that's what we did with Steve in our original paper. And we found sort of optimal choice of these coefficients. And then another thing you can play with is the number of intermediate sweeps you do between time steps. So for some problems, you may only need half sweep. For some other problems, you may need more sweeps. And then another thing that I mentioned before is that the time evolution using Rajikara is non-unitary, and it's pretty dangerous. I mean, there are many papers where people have done this and they did it wrong. Basically, they end up with high energy states. They end up with something totally spurious with no significance. So you have to be very careful. Do it carefully. Study the behavior of the system with the time step. Look at the energy. The energy has to remain constant in time. And another choice is the Krylov expansion, and do the evolution using the evolution operator in a Krylov basis. And at least for the time evolution, that step, I think the Krylov choice is the okay. We have 10 more minutes. In these 10 more minutes, I'm going to talk about the connection with matrix flow states, but only briefly. Right. This is going to be 3 slides. And I'm going to leave this part to Frank Verstraete, who's coming next week. But I think there are some nice connections and nice observations to make. So as we saw last week when Steve gave his talk, his lectures, matrix flow state wave function is written as basically a sum over all the spin configurations multiplied by a coefficient that can be written as a contraction of matrices. I call these matrices A1 with another index S1, A2 with another index S2. If we have a translational invariant system, all these matrices are going to be the same. And we can span this coefficient, and we see here that these matrices have indices, alpha, and we can represent each of them as this diagram that Steve showed last week. So this diagram has 3 legs, 2 for the indices, alpha 1, alpha 2, or alpha and beta, and 1 for the spin where it's acting, or the position in the lattice. So if this is a spin 1/2, this index will have rank 2. Not rank, it's going to be from 1 to 2. And this, the dimension of, or the rank of these indices is arbitrary. You can pick one. It's a variational parameter. It's like our number of states in the DMRG simulation. So this contraction of indices here can be written in a diagrammatic way by putting one of these next to the other. When you connect 2 links, you're basically contracting those 2 links, or those 2 matrices. Now, the evolution in this representation, this is a beautiful representation. This is very elegant. This gives us a fantastic framework to actually do things in a very formal way. So in this representation, for instance, the evolution operator acts on two spins, right? Let's take these two neighboring spins, and it's a matrix and some operator, U. And this translates in a diagrammatic way into this piece to the left, this piece in the center here, and this piece to the right. And this is just some algebra, with this 2x2 matrix. So it's a very simple thing, and it's basically another way to write down what we did before with DMRG. I'm coming to this because Steve asked me to show you a trick he came up with recently, with also it's described in a paper with Maris, where they generalized the Suzuki-Trotter approach for problems that have long-range interactions. In the matrix products representation, actually, this is a very elegant trick. What you have to do is apply swap gates. So a swap gate is a gate, or it's some operation that exchanges two sides, basically, or two indices. So it brings one side from here to here, and another side from here to here. So you can concatenate these swap gates if you will. But imagine here that we want to apply the evolution operator between this spin 4 and this spin 5. So what we do is we sweep 4 and 5, we apply the gate between nearest neighbors, and then we sweep back. We swap back to the original positions. And this is a nice trick that can be implemented if you use this sort of matrix product format. Well, we're done for today. So we're going to discuss next is entanglement growth and different applications. So I'm going to talk about, particularly, I'm going to focus on transport and nanostructures, but other lecturers are going to describe different applications. So things that we can do is we can calculate spectral properties, optical conductivity, photoemission spectra, for instance, by looking at the time-dependent Green's functions. And then we can drive systems out of equilibrium. We can apply quenches. We can bias the system to study transport. We can apply time-dependent Hamiltonians. For instance, we can apply a Hamiltonian that is oscillating in time and look at the response of the system as a function of the frequency of these oscillations. And we can study also the coherence. We can study a system in contact with the path. I look at free induction decay, Haneko, rapid oscillation. We can do pulse sequences to study quantum control and so on. So I think we're done for today. Yes, this is for tomorrow. Thank you.